Lecture is about factors affecting the viscosity of unimodal and multimodal colloidal dispersion. I hope you can learn something from this presentation. So we are going to deal with bimodal suspensions, trimodal suspension, and different distributions. So the keywords would be dispersion systems, colloids, particle size, bimodal distribution, shear stress versus shear rate, and viscosity. I'm going to start with giving you a brief outline of what's going to be covered in this presentation. I'm going to start with some preliminary concepts about dispersion systems, then the introduction, after that equipment and procedure used in this paper, and results and discussion, which is the most important part of this article, and at the end, conclusion and some future directions for people interested in more research and detail about in this field. It's actually about dispersion system. And dispersion system, we usually have a disperse phase that is going to be dispersed into the media called the dispersion media. We can classify this by with respect to different characterizations. For example, physical state and size of dispersed particles. If we are classifying them on the basis of physical state, that would be foams, emulsions, aerosols. And with respect to size of dispersed particles, that would be molecular dispersion, colloidal dispersion, and coarse dispersion. Here we have a concentrated suspension, usually highly viscous, and the aim is to reduce the viscosity by using blends of 2 or 3 particle size. So here the size ratio, weight ratios of two sizes, and absolute size of particles are all important and impactful in this viscosity reduction. Limiting range of particle concentration in unimodal suspension to flow is in the range of 60 to 68% by volume. In these kinds of suspension system, usually hydrodynamic forces and colloidal forces are two major influential forces. Hydrodynamic forces would be fluid shearing or pressure, and colloidal forces would be electrostatic interaction and van der Waals forces between particles. Faris, on his article about suspension rheology in 1968, stated that when we have a unimodal distribution of particles, mainly composed of spherical particles, and the only important force is a hydrodynamic force, the rheology of the system can be calculated only with respect to particle concentration. And this comes to mind from the fact that, when we have monocyte particles, these monocyte particles can accommodate other smaller monocyte particles in the interstices between them. You can think of it as a pool filled of balls, and there are some spaces between the different balls so you can accommodate other balls into them. Hydrodynamic interactions are not only a function of the distance between two adjacent particles, and not only on the characterization lengths of the ball, such as the diameter, but on the ratio of them, and it is actually equal to a function of volume fraction. This function represents the relationship between how different particles are packed together. But in this case, in this article, we have submicron size particles, and in that case, H over D is usually less than 10. And this results in strong colloid chemical forces of attraction and repulsion, and in turn it will lead to typically non-Newtonian fluid flow response when the viscosity is increased with particle size reduction. So Faris's master curve is not adequate for modeling these kinds of systems because it only accounts for hydrodynamic interactions. I will talk about this Faris master curve a bit in the consequent slide, but I won't go too detail in that because it's out of the scope of this mini lecture and it takes time. So different researchers in the literature try to extend the concept of Faris from unimodal dispersion system to bimodal dispersion system, etc. For example, Steinman and Profstein tried considering smaller particles with strong colloidal powers and large particles with hydrodynamic effects eminent. And they came with the result that colloid particles led to non-Newtonian response, and adding larger particles increased the viscosity. But they didn't show how the minimum viscosity is influenced by colloidal chemical forces of interaction between different particles. The measurements here in this article is done but using cone and plate rheometer, Weisenberg rheogenometer, model R16. And as you know, when always we are working with the cone and plate rheometers, there are always this possibility that there would be some sample loss, so it is constantly purged with nitrogen saturated with water to ensure minimum water loss, and the samples had high resin concentrations as the particle size. Let's start with the unimodal dispersions and see the effect of volume fraction of resin on viscosity. So now we are working with two unimodal suspensions with different particle sizes. This figure 3 and 4 is about this. So the particle size is fixed, for example, 0.21 microns and 0.95, and we change the volume fraction. Then we plotted the relative viscosity versus shear rate. Relative viscosity is defined as the suspension viscosity divided by the suspending fluid viscosity, and shear stress is suspending fluid viscosity times shear rate. So as we expected, when we increase the volume fraction from, for example, 0.35 to 0.60, the relative viscosity would be higher. There's a shear thinning behavior at higher volume fractions, and also it is good to note that at 0.35, the lowest volume fraction, it shows some Newtonian behavior because it doesn't change with the change in shear stress. And in this case, we increase the particle size to 0.95, and we can see that the sharp difference in the volume fraction is not sensed and reported here. But still, we have that strong shear thinning behavior at higher volume fractions. And we also see that approximation of Newtonian behavior for 0.35. So at the size of particles, when the size of particles increase, the space between them decreases, and the colloidal chemical forces come into play. They raise the viscosity. So in the next experiments, we fix the volume fraction into the two different values, 0.35 and 0.55. We change the sizes this time, and we can see that when the volume fraction is not so high, the effect is not so much tangible. But when we raise the volume fraction to 0.55, for example, we can see that with the increase in particle size, there is a slight decrease in relative viscosity. So figure 5 and 6 represent different unimodal dispersions and different volume fractions. When the particle size is gets more important at higher volume fractions, higher resin levels, and it's the direct consequence of the increasing influence of colloid chemical forces. When size of the particles is diminished, particles are more closely attached to each other. There's fewer space between them, and this results in higher colloid chemical forces. So for resin levels above 60% volume, monocyte suspensions show bean cam behavior in the sense that they wouldn't flow over gravity, and this can be overcome by using bimodal particle size distributions. So in the next set of experiments, we are going to investigate the effect of bimodal distributions. As you know, there are two different size of particles. We can accommodate the interstices between them to get other particles in the space. Different tests were run on the suspension on different volume fraction levels, and in all of the cases, dispersion showed that shear thinning behavior, and always there was an optimum weight ratio with the lowest viscosity attainable with two sizes. So we are going to look for that range of weight ratio that the lowest viscosity is achievable. Here in figure 7, we can see that for a fixed volume fraction of 0.6, we tried different weight ratios for two particle sizes, 0.68 large particles, 0.21 smaller ones. It is with respect to the larger one. For example, in this plus ones would be 19/10. It means 90 share of large particles to 10 of smaller ones. When we started with the smaller particles, the relative viscosity was high. It failed for when we added larger particles onto a point. For example, here it's about 70/30. But further increasing the larger particles results inversely, and their relative viscosity increases. So in this next figure, it's about figure 8, is the effect of relative amount of large particles in bimodal suspensions containing 0.68 and 0.21 microns particles on the viscosity. So we can see, for example, let's start with fixed volume fraction of 0.65. We can see that when we increase the larger particles, there's the reduction in relative viscosity until a level about 0.6 to 0.80, and then further increasing the ratio of larger to smaller ones results in higher relative viscosity. So we are looking for these minima and this range of ratio between larger particles to smaller particles to achieve the lowest relative viscosity possible. And it is good to note that these samples marked with P are for the suspensions that don't tend to flow under gravity. And again, here the same figure is also plotted in another shear stress. It's 1 N per square centimeter, which is actually when we are working in CGS system, the unit of force would be N. And the lowest level of viscosity attained if we are working with the ratio in the range of 65 to 35 to 80 over 20 with respect to larger ones to the smaller ones. So proper control of the ratios is really integral to get that uh, lowest viscosity. So one might say that why not trying to uh, accommodate much smaller ones. For example, a smaller particles should do a better job filling in the cavities. But also it should be taken into account that packing consideration may also result in colloidal chemical forces. And these colloidal chemical forces are a strong function of the size. So we can increase size ratios in two means, by increasing the size of larger particles or by decreasing the size of smaller particles. When we are decreasing the size of smaller particles, we are decreasing the viscosity by the principle mentioned above, but we are also increasing the viscosity caused by the rise in colloidal interaction between particles. So while when we want to increase the size ratio, we always go with the first approach by increasing the size of large particles. And these colloidal chemical forces are a strong function of particle size, as mentioned earlier. So this is actually Paris calculated care for other distributions, for example, trimodal, tetramodal distribution of particles. It may be concluded that a trimodal distribution would be helpful in reducing the viscosity if the amount of particles in the suspension exceeds 50% by volume. But it is contraband because we should also consider colloid chemical interactions if a trimodal distribution is going to be implemented by adding small particles less than 1 micron in size. And also it is good to note that the difference between unimodal and this bimodal change is much more than the difference between tetramodal, for example, to trimodal. So at the end, what we can give in conclusion is that when we have a concentrated dispersion, it is colloidally stable and the particles are in submicron in the fluid media. Volume fraction of particles, the particle size, and the particle size distribution are all important factors in determining the flow behavior of these systems. And when particles make up more than 55% of the total volume, bimodal distribution can do better in enhancing the flow properties and reducing the viscosity. So about the future direction, what came into my mind is these points. Some analysis of time dependency for multimodal distribution can be one approach, for example, using a stress step increase test, or we can gather some other solid experimental data about trimodals and higher size distribution because it wasn't represented in the paper. They might not be useful reducing the viscosity, but it's worth analyzing them thoroughly. And also another approach would be determining the yield stress for samples that showed being and fluid behavior. Thanks for your attention. Take care.